What quietly powers our homes, factories, and even electric cars? The induction motor, Nikola Tesla's revolutionary invention. In the late 1880s, Tesla envisioned a world powered by alternating current, or AC, and his induction motor made it possible. Unlike earlier motors with brushes that wore out, Tesla's design was simple, reliable, and efficient. While others clung to direct current, Tesla saw the future in AC, which could travel long distances and power entire cities. His induction motor was the breakthrough that won the war of the currents and built the foundation for our modern electrical grid. The genius of Tesla's motor is its simplicity. No brushes, no sparks, no constant repairs. Instead, it uses magnetism to spin. No touching parts, just science in action. This made electric motors cheaper, safer, and more durable, opening the door to endless applications. Today, from the hum of your fridge to the smooth ride of an electric car, Tesla's induction motor is everywhere. It's the unsung hero of our technological world, a century-old invention still powering our lives. In this video, we'll explore how it works, why it matters, and where you'll find it running the world around you. Let's dive into the story of the induction motor and discover the quiet force behind our modern world. Imagine a day without induction motors. No running water, no cool air, no fresh food. These motors are the invisible engines of daily life, working so reliably we barely notice them. In industry, they power conveyor belts, pumps, fans, and the machines that make mass production possible. Escalators, elevators, washing machines, even amusement park rides depend on induction motors. Their secret? Few moving parts, high efficiency, and low cost. They run for years with little maintenance, converting electricity into motion with minimal waste. That's why induction motors dominate: reliable, efficient, and affordable. They're the quiet champions, powering our civilization forward, all thanks to Tesla's brilliant idea. So, what exactly is an induction motor? It's a type of AC electric motor, powered by the same alternating current in your wall outlets. Its magic lies in electromagnetic induction, using changing magnetic fields to create motion, with no physical contact. Michael Faraday discovered that a changing magnetic field can induce current in a nearby conductor. Tesla's motor flips this. AC power creates a spinning magnetic field in the stationary part, the stator. This field sweeps across the rotor, inducing currents that create another magnetic field. The rotor's field chases the stators, spinning the shaft and doing useful work. No brushes, no friction, just elegant physics. That's why induction motors are rugged, low maintenance, and self-starting. They run at steady speeds and power everything from tiny fans to massive pumps. Simple, robust, and endlessly useful. That's the induction motor. Every induction motor has two main parts: the stator and the rotor. The stator is the stationary outer shell, packed with coils of copper wire. When AC power flows through these coils, the stator creates a rotating magnetic field. Inside sits the rotor, a cylinder of steel with conductive bars, usually aluminum or copper, set along its length. The rotor isn't wired to power. Instead, the stator's magnetic field induces current in the rotor's bars. Most motors use three-phase power, with three sets of stator windings arranged to create a smoothly spinning magnetic field. The rotor's bars are connected at the ends, forming a squirrel-cage that chases the stator's field. This interaction spins the rotor and the shaft, powering whatever is attached. No direct electrical connection, just magnetism at work. The result? A simple, durable machine that keeps turning year after year. Stator spins the field, rotor chases it. That's the heart of the induction motor. Simple, powerful, and everywhere. How does the stator create a rotating magnetic field? It's all thanks to three-phase AC power. Imagine three electrical signals, each peaking in sequence, fed into three sets of stator windings spaced around the motor. As each phase peaks, it creates a magnetic field in a new direction, making the overall field appear to spin around the stator. This happens incredibly fast, 60 times per second in North America, 50 in Europe. The result is a seamless, invisible force sweeping around the motor's interior. The speed of this field, the synchronous speed, depends on the AC frequency and the number of stator poles. For example, a 2-pole motor at 60 Hz spins at 3,600 RPM, a 4-pole at 1,800 RPM. This predictable speed is why induction motors are so useful in industry. No moving parts in the stator, just pure coordinated electricity creating motion. That's the brilliance of Tesla's design. The stator's rotating field sweeps past the rotor, inducing current in its bars. This current turns the rotor into an electromagnet, which tries to catch up with the stator's field. But the rotor can never quite match the field's speed. If it did, there'd be no changing field, no induced current, and no torque. This difference in speed is called slip. Slip is essential. It's what keeps the motor producing torque. In most motors, slip is just 2 to 5% of the synchronous speed. That's why a motor rated at 1,800 RPM might actually run at 1,750 RPM under load. Slip is the secret ingredient that keeps induction motors spinning. Most induction motors use a squirrel-cage rotor, aluminum or copper bars cast into a steel core, forming a rugged, maintenance-free cage. No brushes, no slip rings, just reliability and efficiency. Squirrel-cage motors are perfect for steady-speed jobs, fans, pumps, conveyors. But what if you need more control, especially at startup? Enter the wound rotor motor. Its rotor has wire windings connected to external resistors via slip rings and brushes. This setup lets you adjust starting torque and limit inrush current. Ideal for heavy loads like cranes or mills. Once up to speed, the resistors are bypassed, and the motor runs like a standard squirrel cage. Wound rotor motors are more complex and need more maintenance, but offer crucial control for tough jobs. For most uses, though, the simple squirrel cage design wins. It's the workhorse of industry. 2 designs, 1 principle, magnetic induction. Starting an induction motor can be tricky, especially for big machines. Standard squirrel cage motors draw a huge surge of current at startup, up to 8 times their normal running current. For small motors, that's fine. For big ones, it can stress the grid and the machinery. The simplest start is direct online, full power, full torque, full inrush current, best for small motors. For larger motors, star-delta starters reduce starting current by connecting windings in a star pattern, then switching to delta once up to speed. Modern solutions include soft starters, which gradually ramp up voltage, and variable frequency drives, VFDs, which control both voltage and frequency. VFDs offer smooth starts, full torque at low speeds, and precise speed control, saving energy and protecting equipment. These smart starters make induction motors even more versatile. From brute force to high-tech finesse, there's a starting method for every need. That's how we keep the world spinning smoothly. Over a century after Tesla's invention, the induction motor is more vital than ever. Its ruggedness, efficiency, and low cost have made it the king of rotational motion. Today, advanced induction motors power electric vehicles, delivering instant torque and even recapturing energy through regenerative braking. Paired with variable frequency drives, they save massive amounts of energy in everything from HVAC systems to industrial pumps. Modern induction motors convert over 95% of their electricity into useful work, crucial for sustainability. They're a key tool in reducing global energy use and fighting climate change. Quietly, they spin turbines, pump water, build products, and drive our cars. Tesla's simple idea became the invisible heart of our technological world. The induction motor, a legacy of genius, still running the world, quietly, reliably, every day. And that's the story of the unsung hero behind our modern lives.